Welcome to part 2 of fluid dynamics quick revision note. This video's topic is fluid statics. Terminal velocity v is maximum velocity of a body. If acceleration is 0, then net forces are 0. Supposedly, if a body is flowing in a fluid with a velocity v and it is falling, this is a body of mass m, and frictional force is acting on it. Frictional force is tau into contact surface area. Tau we know is mu du by dy into contact surface area A. So net forces is 0. So balancing the forces, weight minus frictional force tau A is 0. From here our terminal velocity comes out to be mg by mu A into dy. Next we have buoyancy and flotation. Buoyancy is basically for completely submerged body and flotation is for partially submerged body. Force of buoyancy is upward force, which is equal to the weight of fluid displaced by the body, or buoyant force is also known as the upward force on an object exerted by the surrounding fluid. So FB, which is buoyant force, is rho g A into h, area into height. Height is the height of submerged fluid. So this comes from mass we know is equal to density into volume. This is density and volume is area into height. So from there buoyant force comes out to be rho g Ah. Then for a fully submerged body, B is center of buoyancy, and for a floating body, M is metacenter, the point at which body starts oscillating when tilted by a small angle. Then for stability of a submerged body, B is we know is center of buoyancy, G is center of gravity or center of mass. So for a stable equilibrium, B should be above G. In all the cases, weight is equal to buoyant force of the body. So for stable equilibrium, B should be above G for submerged body. And when B and G are both at same point, then it is neutral equilibrium. And if G is above B, in that case it is unstable equilibrium. In case of floating body, for stability of floating body, the metacenter, which is M, denoted as M, should be above G, and it is for stable equilibrium. For neutral equilibrium, metacenter and G are at same point, and if metacenter is below center of gravity, in that case it is unstable equilibrium. And the distance or height between metacenter and center of gravity is called metacentric height. It is distance between metacenter of floating body and center of gravity. For floating body, buoyancy act at point of centroid of displaced fluid. Then we have Archimedes principle. It is valid for both floating body and fully submerged body. So this is diagram of floating body. G is center of gravity, FB is buoyant force, W is weight, and for fully submerged body, FB is for buoyant force, B is center of buoyancy, W is weight. So Archimedes principle state that buoyant force is equal to density of fluid into volume of displaced fluid into G. It is equal to density of body, volume of body, and G. So if this is our system and this is the body, so the volume density of this outside fluid, and the volume which this body is displacing into gravity would be equal to density of this body into volume of this body and gravity. So this is what Archimedes principle of buoyancy is about. Next we have hydrostatic law. It states that pressure intensity increases in vertical direction at the rate of specific width. So it is given as dp by dz is equal to minus rho g, where our z is vertical height and rho is density, and this is valid for both compressible and incompressible fluids. So basically, in a system, z is our vertical height, and if we take height from the opposite direction, in that case we know pressure is equal to rho gh. So in case of pressure, in case of height, dp by dh would be plus rho g. For ideal gases, we know PV is equal to mRT, and volume is inverse of density, so P into 1 by rho would be equal to mRT. Now in this equation, dP by dz is equal to minus rho g. In place of rho, we can put this equation, so we get dP by dz is equal to minus P mRT into g. Now taking P to the other side and dz to the other side, integrating both sides, we get pressure is equal to e to the power minus g RT z. This is valid for ideal gases only. So it comes out to be ln P by P naught is equal to minus gz by RT. Then we have hydrostatic force, which states that force in x direction is rho g ah and in y direction is rho g v, where h is our height of center of gravity, a is projection area, and v is volume displaced. So basically projection area is like, if in case we have a semicircle, its area would be area of semicircle, but this is other projection area, like this whole area, it is projecting whatever area, it is projection area. Next we have Gauss pressure. Gauss pressure is pressure above atmospheric pressure. Absolute pressure is Gauss pressure plus atmospheric pressure. So P absolute would be Gauss pressure plus atmospheric pressure in case when Gauss pressure is more than atmospheric pressure, and absolute pressure is atmospheric pressure minus gauge pressure if in case gauge pressure is less than atmospheric pressure. Vacuum pressure is pressure below atmospheric pressure, and this causes raise in height in column. So in this diagram we have a column, and this is the level of fluid or water in this case, and some other fluid is filled inside the column, and here this vacant space we have vacuum pressure, and this is the atmospheric pressure being applied on the water, and this is the raise in height in the column H. So we have taken 2 points, point 1 and point 2. So specific gravity at point 1 into height of fluid would be equal to specific gravity at point 2 into height of this fluid inside. So it would be specific gravity of fluid which is inside the column into height, this height of fluid would be equal to specific gravity of this water filled inside the tank into height of water, this height, and specific gravity of water into atmosphere H ATM minus specific gravity of fluid into this height would be equal to HA of water. HA is pressure head at A. Then we have Pascal law. It says that pressure exerted at a point in static fluid is equally distributed in all directions, which is P1 is equal to P2, and hydraulic lift work on this principle. Next we have manometer. First manometer is piezometer. So this is a column and manometric column, and here pressure at point A, pressure is PA, so PA would be rho GH. Next type of manometer we have is U-tube manometer. So in U-tube manometer, it is in U shape, and this is point A. Here pressure is PA, and this is submerged in a fluid, and inside it this shaded portion is manometric fluid. Usually mercury is taken as manometric fluid. So this height is taken as Y, this, and then above it this portion is taken as X height, and above it this side is taken as z. So when solving question based on manometer, what we have to always keep in mind is when we are going down, then pressure is added, and when we are going upwards, pressure is subtracted. So basically in this case, pressure at point A plus rho g x plus z. X plus z is this distance plus this distance. So overall this distance would be rho g into x plus 1 plus this portion rho m, because manometric fluid is there, so it is rho m into g into y, this height. Then now we are going in upward direction, so it would be subtracted. So rho m into g into this height y is subtracted. Then again rho m into, sorry, this would be rho only because there is no manometric fluid present here. So it would be minus of rho g x, this height, and it is equal to 0. Next we have differential due to manometer. In this case, manometric fluid is present in this portion. This height is given as z, and from B to manometric fluid height is x, and from height difference between A and B is y. So density of both the side one A and B is given as rho w, and manometric fluid density is rho m. So in this case, then pressure A plus rho w of y plus x plus z, this whole distance. Now we are going in opposite direction, in upward direction, minus of rho m, this portion, into g into z, this height is z, minus of rho w, because here density is rho w, g into x, minus pressure at B would be equal to 0. Inverted differential U-tube manometer, similar conditions are given. So this is point A, point B, both have density of rho w, and manometric fluid have density of rho m. So height between point A and manometric fluid at that side is x, and height difference between point B and manometric fluid at that side is z, and this height is given as y. So we are going to start from this end. Pressure at A minus, so we have already stated that if we are going to go in upward direction, pressure would be subtracted. So in this case it would be PA minus rho w, because density here is rho w, g into x, this height. Then it would be, now we are going to go to the other side, and pressure is going to be added. So this portion, first we have taken this height. Sorry, the diagram is like this, has to be x would be this much height. I'm not good with drawing, so sorry about that. So manometric fluid is only this much height, and both these points are almost parallel. These are not same height. So pressure at A minus rho w g x, this height, plus now we are going to move downward direction, so it would be rho m, manometric fluid, into g y, this height, plus now again moving downwards, rho w for this gz, this is z height, minus pressure at point B, or we can say it is equal to pressure at point B. Next we have fluid kinematics. First, streamline flow. It is continuous line such that the tangent at any point on it shows the velocity vector at the point or the direction. There is no flow across streamline. dx by u is equal to dy by v, dz is equal to dz by w is differential equation of streamline where u, v, w are velocity in x, y and z directions. Flow is steady state and incompressible. Then we have continuity equation. It is important. In two dimension, du by dx plus dv by dy is equal to 0, and its generalized form, it is written as delta p by delta t plus del rho v is equal to 0, and del is for divergence. This is divergence sign. So divergence into v is equal to 0. Del dot v is 0, and del dot v, for flow to be possible, del dot v has to be 0, and this is an incompressible flow. So basically this topic would be more clear to you guys when we would solve practice question based on it. There would be question asking to find if the flow is compressible or incompressible, or if the flow is possible or not possible. And similarly, in case of vorticity, question would be that if the flow would be rotational or irrotational. For those questions, these are going to be useful. So when divergence dot velocity product is 0, then flow is possible and incompressible fluid is there. And in case of flat plate, so this is area of flat plate rho u, which is 2 rho u into area. This would come useful in solving questions when we would solve question. So to find vorticity is curl of vector v, which is 2 times of rotation component. Velocity is given as ui plus vj plus wk cap, ui cap plus vj cap plus wk cap. So cross product of v cross v can be written as ijk del by del x, del by del y, del by del z, u, v, w is equal to 0. And if cross products come out to be 0, then flow is said to be irrotational. And if it does not come out to be 0, then flow would be rotational. And to calculate rotational component of velocity, w is equal to 1 by 2 mod of cross product of v. So this would be more clear to you guys when we would solve practice questions. So make sure you watch those videos to better understanding of these calculations. Next we have shear strain, which is tau is, we know, is equal to mu du by dy, and it is equal to mu d theta by dt. So rate of shear strain we can calculate from there is 1 by 2 del v by del x plus del u by del y. Total acceleration is equal to local acceleration plus convective acceleration. Local acceleration is also called temporal acceleration due to time change and for unsteady flow. And convective acceleration, if with respect to given time velocity coordinates changes or acceleration change with respect to space, that is convective acceleration. It is for non-uniform flow. And ax is acceleration in x direction is taken as du by dt being local acceleration plus u du by dx plus v du by dy, and acceleration in y direction would be du by dt v dv by dx plus v dy by dv by dy. This is u, sorry. So in x direction it is u du by dx plus v du by dy. In y direction it is u dv by dx plus v dv by dy. For steady state one dimensional condition, total acceleration would be equal to only convective acceleration, because in steady state our local acceleration would be 0. So it would be u du by dx, because it is in one dimension only. It would be equal to u2 minus u1 into d of u2 difference of u2 minus u1 upon difference of x2 minus x1. Then to calculate absolute acceleration, which is mod of a, would be equal to under root of ax square plus ay square. And if psi function is given, in that case our u would be minus of del psi by del y, and v would be del psi by del y. And in Lagrangian system, dx by dt is not equal to 0 and dy by dt is also not equal to 0. That is, location change with respect to time, dx by dt is equal to u and dx by dt is equal to v. If velocity is independent of time, that is, in that case it would be steady state flow. And for potential function, potential line is basically same potential is at every point. So potential function denoted as phi is constant. It is function of x dot y, and d phi would be d phi by dx into dx plus d phi by dy into dy is equal to 0, and minus del phi by del x is equal to u minus del phi by del y is equal to v. Slope of potential line given as dy by dx, it is minus u by v. All these formulas would be more clear to you guys when we would solve question. Again, I'm repeating the same point because these are just basic revision formulas, so it would be more clear if you would see practice questions based on these.